right, here we go. Hello, and welcome to this week's security seminar from CERIAS at Purdue University. Our speaker this week is Professor Bruno Ribeiro, who is a CS professor in the computer science department here at Purdue. Bruno?
Thank you, Joe. Thanks for inviting me to give a talk at CERIAS. So here I am going to move forward. I hope that's okay. Welcome. And so today I'll talk about predicting what users will do next. So if you bear with me, let me go through first a general introduction. So here we have an agent that is walking around the world, right? We have, for instance, this agent is walking around Lafayette looking for a coffee shop and then go maybe to a restaurant, or is trying to buy some tablet in a store like Amazon or eBay or Best Buy. Or maybe it's browsing for music. It's building a music list and it's listening to songs in this music, in this website. So what these problems have in common is that once the user reaches a place, you want to know what the user will do next. And so this is the general motivation. So for instance, online shopping, we have, let's say here, tablets and laptops, and you can go to one of them, let's say an e-reader, and then after you click here, maybe you go check how much it costs on Barnes & Noble. Is a different equipment gift card. So these are the users browsing these websites, and so the motivation here is to predict, given that where they are and what they have done, that we know what they will do next. So this is the general problem. Is called predicting user trajectories. Okay, so this is the user trajectory, and the security motivation for this would be, for instance, you have some access patterns. We have a regular user who is accessing some files in his company, and a malicious user that has a different pattern of accessing these files, right? And you want to separate or group the users that are regular users against the users that are malicious, that they have some weird or different type of access pattern. So you just want to group users. Another scenario is where you have a regular user and a VIP user, okay? And the VIP user has access to some other documents. And the patterns that you see from a regular user in your company should be different than the ones that you see from the CEO. But then this account is compromised, and now the regular user is starting to behave like the CEO, trying to get access to this important information about the company. And that's when you realize that the user changed behavior. It's not like a regular user anymore. It's very different. It behaves more like the CEO, and now you can identify this anomalous behavior. Okay? So there are the two motivations in security for this. And a more personal motivation, which often is why we do research, is I had an ebook, and I was sharing this ebook with someone else. And whenever I was browsing, so this is the type of books that I would appear on my recommendation. It's usually science books. And then because I was sharing with someone, I would receive a lot of recommendations of books that I was not too interested in. And what was upsetting to me was that I would keep browsing the books that interest me, and the website would never really learn that I am very different. My trajectory is very different from this other person that was sharing the ebook with me. The other person would do a trajectory over other very different types of books. And the machine learning algorithm that the company was using was not keeping up with this understanding of the trajectories. So here is me browsing, and of course I'm not browsing the other books. So and then when I started looking more into the problem, and a problem that I was already interested, of course, but there were no scalable big data methods to predict this type of navigation, this type of trajectories. And I was surprised, and that was 2015, surprised at the fact that in 2015 we still didn't have any scalable algorithms for this type of trajectory prediction. So there are reasons for that, and I'll show you some of the challenges regarding learning user trajectories, specifically because of user behavior. And that also ties back to security, the way that people access files and the way that they behave in a company is quite complex. So let me give you an example. So one of the first challenges here is account for stationarity. What is that? So you can think the trajectory of the user is a mixture of what we call stationary processes. So what's a stationary process is, we can think of a process or a stochastic process or behavior, right, that does not depend on wall clock time. So if you are browsing on Amazon in the morning for a computer, or if you're browsing on Amazon in the afternoon for a computer, your browsing behavior would be the same, right, because you are trying to do the same thing. So that doesn't depend on wall clock time, and that's what stationarity means. And also the same thing, if you're browsing today, you would have the same behavior as if you were browsing tomorrow, right? It's the same behavior. So that's what the stationary process, there is a more precise mathematical definition, but I'll give you just the intuition behind that. So here we have a process, right, in which you are navigating over documents A, and process B that you're navigating over documents. And if you think about how users behave, you will see that what they actually do is at some point in time, they start behaving like A. And then another point in time, they still behave like A for a while, and then they quit the system, right? They stop, they go home, or they close the website. And now they are behaving like process B. It's a different process. So your behavior online, or your behavior in general, is a mixture of these processes that don't really depend on exactly the date that you started. Some processes do, but a lot of the processes that we're interested in do not depend on the exact time, wall clock time that you started things. So the second challenge is evolving behavior over time, right? So users may not be time heterogeneous, and what that means is that over time you may, for instance, if you like music, you may start here in 2010, you may like classic rock a lot and US pop, and then you're listening to this classic rock and you alternate between classic rock and pop. So this behavior over time is changing, and maybe you add a bit of heavy metal, and then you go back to pop, and etc. The same thing with in the other case here. One interesting aspect is that here time heterogeneity doesn't mean that you will not go back to the same behavior later in the future. You may go back to the same behavior in the future, but that can take a long time, okay? So so you can think of an evolving trajectory. Okay, so an interesting point. So this is annotated data. This is real data from some users at Last.fm. And it's interesting that the user here has US pop. You see, US pop is interested and then start listening to classic rock and then gives up on the pop and then just listens to classic rock after that. Another one, that is one of the more interesting actually, was a mixture of heavy metal, pop, and classic rock, and then switched to Korean pop and never went back just listening to Korean pop. I don't know, when was, maybe that's when Psy came out, I'm not sure. Okay, so I may have been the last person to learn about this. I had a friend who like forced me to. Anyways, so here we have some the third challenge, which is that these trajectories may be transient. So let's say that you go through phases when you listen to music, or you go through, when you think about job, the behavior of people accessing files on a company, when they change job title, they change their access behavior, right? So you expect, for instance, if you, maybe you like music, you like 60s music, and then you are just listening to 60s music. You are 3 years in this span that you are really interested in 60s music, but then you decide to change. As we saw, people sometimes they change to very different styles, and you now you have 4 years of heavy metal that you're really more interested in heavy metal than anything else, and after that you go to your next musical phase. And what is important in the transiency of these processes is that you will never go back to the 60s. Okay, so you are done with that, and now you move on. That makes the learning of this trajectories incredibly difficult, right? Imagine that you have something that people are doing and they will never do again. And in the other case where we have, for instance, here, evolving trajectories, right? So you're evolving over time. So it's hard for you to learn what they are doing if it's not recurring. It tends to evolve and continuously adapt. So let me show you now what the data would look like for this type of problems. So the data is a trajectory. So we have a user, and we have what they access and when. Okay? File A, file B, file C. And this is the observed trajectory data. So this is all we have. All we have is this. And what I'm going to briefly explain is that in machine learning and data mining, what we'll do is, observing this data, we will come up with a model. And it don't have to be, I'm not going to explain exactly how the model works, but you come up with a model that will learn from this data and then make predictions and group users according to their behavior. Okay? So what I'm going to talk about now is how to come up with these models. What are the models and how these models work. Okay. So there are a bunch of naive solutions to the problems if you are familiar with them. So for instance, matrix decomposition, non-negative matrix factorization, or singular value decomposition. You have multiple ways of decomposing this user product matrices. Like, so you have a user, you have a product, and that's often how naively you would recommend products to users. Okay, and these are mostly done in the general idea is to do a low rank decomposition over this matrix. The problem with this approach is that assumes that things are homogeneous in time, so the users are not changing their behavior, and the behavior tends to recur. There is no transiency in your behavior. And another approach is the tensor decompositions, where so a tensor is a multidimensional matrix. So if you understand what a matrix is, you basically understand what a tensor is. It's just that you have one more dimension. So a vector has one dimension, a matrix will have 2 dimensions, and a tensor has a 3rd dimension. You can think of it like a cube, okay, with data. So one of the dimensions can be time, right? So you can have user, you can have product, and you can have time. What is interesting about tensor decomposition with the sign mode is that we'll see at the end that you cannot recover hidden behavior from stationary processes. So the fact that today your behavior is similar to your behavior tomorrow will make it very hard for the tensor to learn your intrinsic properties of your trajectory. Something that you may have heard about are hidden Markov models. Who here has heard about hidden Markov models? Okay, so we have a few. So hidden Markov models, the idea is to model a trajectory. Were very used a few years ago in learning how people write and also learning speech recognition. So these models will model just a single type of trajectory. They are not meant for people with different objectives, right? We have the CEO, we have the regular users, we have the supervisors. So these will be different types of trajectory, and these models are not really meant for this type of data. Okay, so these are the naive solutions that will not quite work well. And recently, there have been a number of other solutions, better solutions to the problem. And one of the most interesting ones is called the Latent Markov Embedding. Was published at KDD in 2013. And there are many other variants of that, multi-core latent Markov embedding and personalized ranking latent Markov embedding, which is the fastest from our simulations with real data. It seems to be the fastest and most accurate of for trajectory prediction that among all of them. Was published last year. There are other methods like factorizing machines. I'm not going to go into the details of how these methods work. I'll just say very vaguely that latent Markov embedding, the idea is just to project your data into a latent space, and then you learn a Markov chain over that latent space. Okay, so one of the common issues for all these tools is that they are too slow for large data sets. Okay, so you cannot learn over larger scale data. So the insight that of our work here is that understanding the constraint dynamics of the trajectory is key to predict the future. So if I could see where the agent is, then it will be easier for me to predict where the agent will be next, because you see, if you are in Lafayette or if you are on a given website on a certain page, it's hard for you to jump to some other place, right? For instance, if you are in Lafayette, you cannot have dinner in New York City. That's very unlikely. The same thing in a page. So if you are on a page where you have a certain group, it's hard for you to immediately after go to something completely different, right? So, but what we see is just what the user did, right? So he was listening to Madonna and then went to listen to Daft Punk. And what we'd like to do is from this observed trajectory, we want to learn what were the constraints. What would be, given that most users did this type of transitions, right, from one artist to another artist, or from one business to another business, or from one file to another file. You want to know what is the kind of space or constrained space that they were living in that forced them to do this type of navigation. And that's what we are going to learn from data. We are going to learn this constrained space. Problem is, the trajectories is really all we see. We don't see the constrained space. We don't see the space. So, and that's what we are going to do is we start with the data and then we reverse engineer the data to get to the constraints and the way that people are navigating over these constraints. Okay? So for the experts, the idea is to learn a navigation process over a network using non-parametric based methods. The learning is 100% automatic, so you just give the data and the method will give you the results. You don't have to, there are no parameters that you need to tune. No domain knowledge, you don't need to understand anything about the data, just throw the data at the model will create the constraints and the navigation. And this work is a joint work with Figueiredo, Almeida, and Falutzos. It will be presented at WWW this year in August, if I'm not mistaken. Okay. So let me give you some more details of how this works. So the basic idea started with with the idea of random walks over random environments. And that idea really, the first paper on this was in, if I'm not mistaken, 1934 from a Russian mathematician describing a model for the DNA, for the formation of DNA, or copying in DNA. And this type of analysis gave us percolation theory. So if you know percolation theory, it came from this analysis of random walks on random environments. So the constraint that I was talking about will be a graph with vertices. The vertices are the products or the files, and the edges are how likely it is that, given the objective that you have right now, that you would, from one file, go to the next file, okay, to another file. Or if you go from one business to another business. Or that you go from one song to another song. For instance, what would be this constraint? This conditional behavior would be, for instance, you love heavy metal. So if you're listening to Metallica, then probably the next one that you might be Iron Maiden. But the link weight or the edge to Madonna is very unlikely, has very low weight. It's very low probability that you go from Metallica to Madonna. You'll be surprised what you see in the data, actually, which is very interesting. But indeed, it's very unlikely that you do that. Now, we have such a graph, and this graph defines one layer of these hidden constraints. So if you like heavy metal, then you have one graph over the whole set of songs that describe how people that like heavy metal will walk on this network. Okay? Now, if you like something else, if you like pop, then there is another graph that is how people walk on this other graph. And this graph, the way that we'll do is to say that these are created randomly. These graphs are, the generative model of this will be that these edges are distributed, the edge weight or the strength of an edge will be distributed according to a gamma distribution. It's just a way to probabilistically describe what you are seeing, so you can reverse engineer it, okay? Now, the way that we're going to work then is to have, let's say, Alice. She really prefers graph G1, let's say heavy metal, and then she does a random walk. If you're familiar with PageRank, anyone familiar with PageRank? Have you heard about PageRank? So PageRank is a random walk, and then you randomly jump to another node. Okay? So what we are going to do is similar to that, in that for graph G1, let's say heavy metal, then she will be walking around the songs according to a random walk determined by the probability that you walk on a given edge is determined by the edge weight. Okay? And then, after a while, Alice gets bored and then randomly jumps to another thing that she likes. Let's say pop, right? And then she likes pop, or if she likes other type of heavy metal, she can also jump to other type of heavy metal. So this is the model. This is what we are trying to learn. Okay, so we give a probabilistic description of this model and then try to learn the parameters of this model. Even more details. So what we'll call the environment is a mixture of this latent structure that we are trying to learn and a navigation process on top of this structure. The navigation process is given is a random walk with jumps. And then what we assume is that users behave like this, so there is a latent structure, there is a navigation process, and what we see is these trajectory segments, right? We are going from Britney Spears to something else, a Metallica, to Iron Maiden, and etc. And now we want to learn back what the user preferences are. And the preferences are over the environments are learned assuming a Dirichlet process over the different environments. So you can have, what is interesting about assuming a Dirichlet process is that you can have the method automatically learns how many of these environments or these constraints or these interests that the user have exist automatically. You don't have to tell that in advance, okay? And then you have whenever you have a jump from this random surfer, so you're randomly surfing over this network, let's say heavy metal, you change not only the node, but you also change the environment. And you go to another preferred environment according to the probability. So the 0.3 and 0.6, there are the probabilities that, that Alice will jump to one of these other environments. Maybe it's trash metal, maybe it's pop, maybe it's something else that she prefers. Okay? So how do we learn the model? Even more details. We use Gibbs sampling, and the idea to make it fast is to use stochastic gradient descent for fast convergence in mini batches. So use a split and merge heuristic to learn the Dirichlet process, and a heuristic for learning trajectories over fixed size renewal points that makes this learning process extremely fast. Let me show you the results with real data sets. And first I'll show you the data sets. We have 3 types of data here: music streaming services, where users are listening to songs; location-based social networks like Foursquare and Brightkite. I don't know if you're familiar with Foursquare. You choose, which is something similar to Amazon. People or Best Buy, people are clicking on products. And yes, which is also kind of an internet radio station. Okay? The largest data set is less FM groups, where we have 86 million transitions, different jumps between different artists, and 1.6 million artists in this data, with about 15,000 users. Okay, so how does this idea or this method will do in this approach? So what we'll see is what we are looking here is in the x-axis the running time, how long it takes to learn this model over the data. And in the y-axis is a measure of accuracy, how accurate you are in predicting what the next thing that the user will do. Okay? So the best possible approach would be at the left upper corner. Okay? You learn very fast and your accuracy is very good. At the bottom is the worst. At the bottom right is the worst, where it's going to be very slow and your accuracy is not good. So our approach, what is interesting is that our approach can learn the model in up to 16 hours. So the one thing to notice is that the x-axis is in log scale. So here is 1 day, and then you have here 10 days, and this is over 10 days. And we could not get the competing methods to finish in 10 days, just trying to run over the same data set, not even the smallest one. One that our method takes 1 hour, it takes more than 10 days for the competing methods. And multi-LME, our prediction is that it would take 6 years to learn over the largest data set. And so that's one of the reasons why we don't see a trajectory prediction in commercial services, is because the methods haven't been, my hypothesis is that the methods have been fast enough. But our method now is fast enough. So to be fair, right, maybe they are slow, but they are very good. It could be that the accuracy is better, just that they are slow. But what is interesting is that if we cut these other data sets, we subsample them, and then feed them to our method into the other competing methods, we'll see that our method, which we call tribe flow, is still significantly faster. In this case here, 46 times faster, and always more accurate. It's not only faster, but it is more accurate than what's out there. So, and this is basically the best competing approach is 46 times slower. Our method is 46 times faster and 23% more accurate. So, Another interesting aspect, I was talking about tensor decomposition, right? If you think about a tensor where the products are one of the modes, the users are in the other mode, and the third mode is time, okay? So it's this cube. And then the tensor decomposition will decompose this into 3 matrices. This is an example of Tucker decomposition. And a matrix in the middle there. That is a matrix that can mixture the different other matrices. So if we try to learn using tensors, the hidden structure of this data, the real hidden structure of the data. So we have here generated data that is coming from a stationary process. And we use one of the very good method for learning over large data sets, which is try-mine. And we see that this is the truth. So the y-axis is the type of behavior that the process has. And the x-axis are the users. So there we have 10 users with one type of behavior, 10 users with another type, and etc. So we have 5 different types. And then we make them perform their trajectories over different points in time, right? Like you do it today. Maybe another user that's similar to you will do that trajectory tomorrow. So if you try to apply tensor decomposition, you see that you don't recover the behavior of the users very well. But with TribeFlow, we can recover it quite well. Now, there is another benefit. So one of the benefits of our model, and the idea that you're modeling these constraints and the navigation over this constrained space, is better sense making. So here we have Foursquare data. And in general, what you would do is to have kind of a Gaussian or some distribution of spatial distribution over your data to say, well, if you went in Lafayette, then you're probably going to go around the area, right? That area. For the next point of interest. Our method learns this constraint automatically from the data. And what is interesting is that the method outputs something like this. It tells us that domestic flight, so it appointed us to a group, to a constraint, a spatial constraint, that are airports in the US with Foursquare data. And these airports are domestic airports. So if you hit a hamburger in LaGuardia, maybe you eat you have a drink, a Coke, in Indianapolis. You see? It's not spatial. It's learned that there are some places that have this connection, this constraint connection, which are these airports, local airports. Moreover, it also found some other examples. I'll give you one. Pacific airports and the US and UK hubs connecting Asia to Europe and the US. So if you have some food, McDonald's in New York City, JFK, it will predict that your next meal will be in Beijing. Okay? So another interesting aspect of this approach is to understand the data over multiple resolutions. So here, this data here that I was showing to you, users were liking, they like classic rock and they like Korean pop and etc. This is automatically learned by the method. Okay, so this classification and the way in which people are changing things, you can see that the method can tell you when they decide to switch from pop to classic rock. And these are some examples of some of these hidden networks or hidden constraints that it learned. So one hidden constraint, if you like some movie soundtracks, then you have this composers that of soundtracks, movie soundtracks. And if you like thrash metal, then you will go over these different bands. I did not do that. The student did, because I don't really know many of these classifications. So So Iron Maiden, Slayer, and etc. So if you learn that these are constrained because users tend to do trajectory over these specific items together. Okay, we have 90s rock, Nirvana, Green Day, and electro house, which is a very specific. Actually, it divided in many different types of house, and what I found online was that this seems to be electro house, and this is all automatically done. So if you have any questions, I'm happy to answer the questions. I'm open to questions. Any questions? Or like if you have ideas about types of data or applications to this type of method? Yes?
So the model over here seems, so model seems to learn by studying the trajectories of where the user goes. Don't you think it'll raise privacy concerns with certain users?
Privacy concern. You see, in data mining, we have a different view. We want the data. Regarding learning, how can you learn this privately, right? So an interesting aspect of this trajectory learning, and I have worked on this before, so I know that you might be able to identify, is that you don't really need to tell me anything about the item that the users are visiting. You just say it's item number 32. You can totally anonymize the item number, and you can anonymize the user. And then I'll give you, well, item 32, 44, 55 are together, and user 155 tends to go over these items together. Of course, if you know that you can always de-anonymize this type of data, but it doesn't really need features of the user. Let's say the age or any other, or where they live, and etc. It just learns over this abstract concepts. Any other questions? Yes.
I want to know what's your intuition behind that is faster?
Oh yeah, the microphone there.
I wonder what's the intuition behind your method is faster than others, because from my point, I'm not very familiar with all the machine learning algorithms, but to me it's like you are trying to find some latent factors, while the others methods, some of them are also trying to use some embedding methods to project to the low dimension space. So I wonder why your methods are much faster than others.
That is a very accurate description of what they're doing, right? So if you can put a lot of the machine learning methods as trying to learn latent factors. And we are indeed trying to learn latent factors, but there is one interesting aspect. If you give more structure to the problem, then learning tends to be easier.
Oh.
The more degrees of freedom you have, the more the space that you have to search, it becomes a bit harder. And the interesting thing is that if you have a good insight of what the structure is like, you will actually learn better than you would if you had something that was more generic. And so the big insight here is that users, when they are doing these trajectories, they are doing over this constrained space. And the way they are navigating, we determine that way to be very simple. It's like a random walk. The hard part is just to learn what the constraint looks like, okay? While oftentimes what we'll do is to have the process in which they are navigating to be the complicated one, and the space to be very simple. So we inverted the problem. We said the navigation is very simple, the space is a bit more complicated. And it seems to match very well the way that you would actually behave, right? It matches intuition of what the structure of the problem should be. If you're in Lafayette, then you have some spatial constraints that you can't get around, and that will show up on your trajectory. But what's interesting is that the spatial constraint is not just spatial in the sense of distance in miles. You saw the airports, right? If you're an airport, your space constraints change. From the airport, you cannot go to Lafayette very easily. although it's close in distance, but it's much easier to go to New York City, right? So that is, I think, one of the reasons why our method is so much faster.
Thank you.
Any other questions? Any ideas of data or behavior that you would like to capture? Security behavior? Okay, well, I guess there are no other questions. I'd like to thank you for your time, and I'm available offline also if you want to ask things off the microphone. Thank you.